Ah, Earth. The third rock from the Sun. The blue planet. You get it. Its atmosphere is made up of around 78% nitrogen, 21% oxygen, and 1% argon, water vapor, and carbon dioxide. A nice balance for any living creatures to breathe. The weather here is also perfect for life to exist, unlike places like Saturn, Mercury, or any other celestial object in our solar system. We have the troposphere to thank for that. It's the densest part of the atmosphere on our planet and is 5 to 9 miles wide. It's the layer of the atmosphere that always affects our weather and secures the right conditions for life to exist and to have bodies of water. Earth is just sitting in its orbital path, minding its own business, revolving around the Sun until, BAM! Venus and Mars swoop in and spoil the fun. No one wants to leave poor Earth alone. These two relatively large celestial objects moving toward Earth will have dire consequences for our planet, starting with changes in its orbiting trajectory path. The planet's orbits in the solar system have to maintain the right balance so that nothing goes haywire. Of course, if any large object approaches Earth, it would throw our orbiting path off course. The planets will revolve around each other, which will cause plenty of natural disasters on our lands. This will also affect our rotation timing, potentially slowing it down. Days will not flow but drag by. Animals that rely on daytime will need to readjust their biological clocks. Nocturnal animals will also need to figure out how to cope with the long nights. Humans have adjusted pretty well to the 24 hours a day timing. Time itself is just a human construct to measure things. We'll have a tough time sleeping and adjusting to the stretched day. Marine animals rely on the natural current flow to migrate around the oceans. With Mars and Venus crashing the party, it looks like they will also need to find new paths. Birds migrating to other lands throughout the year will also be confused and not know what to do. In general, the Earth's temperature will rise, and massive heat waves and permanent climate changes will occur. This brings us to our next issue, the heat. The radical temperature rise will turn everything into a barren desert. It'll be summer all year long, especially if Venus is in the picture. Most of the planet will dry up and won't be suitable for growing crops. Venus is hot, really hot. Even though it's not the closest planet to the Sun, it's still the hottest. The temperatures on Venus are close to 900 degrees Fahrenheit, which will melt you like an ice cube. The lands on Venus are generally flat, probably due to the temperatures. It's mainly hot because its atmosphere is thick and traps the hazardous gases inside. If Venus inches its way towards us, it'll invite those gases to our atmosphere and compromise it. Mars, or the red planet as we know it, is very cold. That might stay the same if it starts rotating around us. It's also home to the largest dormant volcano in our solar system, which makes Mount Everest look like a tiny bush compared to a tree. With so much instability, it might just wake up one day and spew out molten lava. Mars has a very thin atmosphere, which makes the planet chilly. Its gravity is quite similar to ours. It's actually very cold and has ice caps in the poles covered with carbon dioxide. The same's true for Mercury. You can only last there as long as you can hold your breath and be in the sweet spot between the sunrise and sunset. The three planets orbiting each other will eventually collide. It's just a matter of time. And the Moon, just hanging out like a fly on the wall, will be so insignificant that something will eventually throw it off course and another planet will capture it to its orbit. Or, in the most dire case, it will collide with one of the two intruding planets. Earth will experience extreme tidal waves like nothing before. The two new planets revolving around Earth will cause a major imbalance, making our gravity shift out of control. Each tidal wave will be bigger than the previous one and will cover the dry land. Plenty of little scattered islands in the oceans will be completely submerged. Coastal cities and towns will also be home to fish. Flat countries in general will need boats to get around. Dams and dikes won't be enough to stop the water from coming in. Everyone needs to move towards higher ground to escape the floods. With the climate getting hotter, the polar caps will melt like ice cream on a sweltering summer day and add to the water level rising. Within a few months, the whole Arctic will be nothing but liquid. But wait, there's more! The crust will wear out due to the instability of the Earth's surface and fluctuating gravity. The Earth's crust is mainly made up of oxygen, which means we're basically walking on air. We might experience more earthquakes than before, and dormant volcanoes will wake up from their deep slumber. The skies will be covered in ash, making flights impossible. No one can travel by sea or by air. Importing and exporting will become history. The overall climate will get hotter, just like in Venus. The three planets orbiting each other and their huge mass might even unintentionally welcome other planets and celestial bodies to join the party. So, what if Jupiter decided to turn up? Now, Jupiter is the largest planet in our solar system. To give you an idea, the Earth would be just the size of a grape if Jupiter were the size of a basketball. It also has the largest storm we can perceive. That's known as the red spot, a place twice the size of Earth that has hurricane-like storms that have been going on for hundreds of years. Now, by the time you're done watching this video, you can expect the storm to still be going at it. Since the planet is huge, gravity must be quite strong here. It also has many moons, some of them of our little Earth. There will be no room for any proper space among the planets. Jupiter's moons will be thrown off course and latch onto other planets around. Some of the moons might collide with each other, causing massive debris to be displaced all over the place. The gravity of the planetary party will attract comets to enter the atmosphere, potentially crashing down on us. Oxygen levels will deplete, so the Earth's crust crumbling will continue. It'll rip open the ozone layer, causing heavy strokes of ultraviolet waves to enter our atmosphere. We won't be able to step outside for too long without some protective gear and oxygen tanks. Human civilization will change drastically. We'll all live in sheltered containers that will provide clean air and safe and filtered sun rays. The shelters will be sturdy enough to withstand frequent earthquakes. We will grow only enough crops to sustain ourselves until we leave the Earth. Since it'll only be a matter of time before the planets collide, the next step would be to create large rocket ships to fly us out of the Earth. With Mars, Venus, and Jupiter revolving close to us, it won't be easy to do so. All the space debris will be blocking us from exiting the space zone area. The only safe place outside this region will be many millions of miles away, where only single planets exist. They may or may not have the conditions to host life, but humans will have the technology to land just about anywhere with similar gravity and construct the right shelters. Eventually, Mars, Venus, Earth, and Jupiter will collide with each other and break like eggs, like a big space omelet. Don't forget the moon's crashing and breaking in the mix, but we'll already be far, far away by then, hopefully. You know, rotation is a funny thing. Not haha funny, but kind of strange. Not only can't you feel it, everything does it. From galaxies to atoms, the universe is taking us for a spin. Strangely, it was more difficult to prove that the Earth is rotating than it was to prove that the Earth is revolving around the Sun. Way back in 1610, Galileo, the father of experimental science, provided the first proof that Earth, and all the other planets, revolve around the Sun. Galileo showed in his telescope that Venus was going through phases like the Moon. The only conclusion possible was that Venus was revolving around the Sun. Case closed. Planets revolve. But it wasn't until 241 years later, March 31, 1851 to be exact, that Leon Foucault proved that Earth was rotating. Foucault installed a giant pendulum from the 220-foot high ceiling of the Pantheon in Paris. That's a lot of peace. An assembly of scientists and journalists watched as the floor turned beneath the giant pendulum. "The Earth turns," they shouted, mostly in French. Another strange thing about rotation is that although the Earth is rotating at a constant speed, the surface of the Earth is moving at all different speeds at all different latitudes. The same is true for every planet and star. At the equator, the surface of the Earth is moving the fastest at 1,037 miles per hour. That's much faster than the speed of sound, which is a mere 761 miles per hour. Halfway from the equator to the North or South Pole at 45 degrees latitude, the Earth is rotating at 733 miles per hour. Standing at the North or South Pole, it would take you 24 hours just to turn around one time, and that's both boring and cold. One result of these differential rotational speeds of Earth is that it creates belts and bands not only in the atmosphere, but also on the surface of the Earth. Jupiter, of course, is famous for the belts and bands in its clouds caused by the giant planet's rapid rotation of about 28,000 miles per hour. The belts and bands on Earth's surface are somewhat overlooked, but we've got them too. We have white ice at the North and South Poles, and between the two poles, there are alternating belts and bands of dry sandy desert and moist green vegetation. This essential geography can be seen most clearly when we view the Earth rotating in space. Space agencies use the differential rotation of the Earth to their advantage. They launch their rockets as close to the equator as possible. NASA uses Cape Canaveral near the southern tip of Florida. And the ESA, the European Space Agency, uses the Guiana Space Center in French Guiana, South America, almost exactly at the equator. Because the land under a rocket near the equator is rotating at a greater speed, it gives the rocket a boost into space that launch sites near the poles cannot provide. You always want to save fuel, you know. Speaking of Jupiter, as I did about 3 paragraphs ago, the axis of rotation of the big planet is even less inclined than that of the Sun. The Sun is tilted at an angle of around 6 degrees, while Jupiter is only tilted 3 degrees. Jupiter stands almost perfectly upright, which combined with the great speed at which Jupiter is rotating, its entire day is less than 10 hours, it turns Jupiter into a giant gyroscope. Jupiter's gyroscopic stability, combined with its massive gravity, gives stability to the whole solar system. Jupiter prevents chaos factors from disrupting the orbits of the other planets. In other words, without Jupiter rotating like a stable gyroscope, the solar system could never have stayed intact for the billions of years that it has. Exoplanet solar systems are showing signs of chaos in their orbits. They could use a gyroscope like Jupiter to hold them together. Rotation is the real hero here. As for the Sun, its differential rotation has a big effect on its sunspot activity. Sunspots are spots or patches that sometimes appear on the Sun's surface, usually at mid-latitudes in both the northern and southern hemispheres of the Sun. As sunspot activity increases on the Sun, sunspots begin to move closer to the equator. Few sunspots are ever seen near the poles. With differential rotation, the gases at the equator of the Sun are moving faster than the gases at the Sun's poles. This differential motion of the gases twists the magnetic field lines in the Sun, causing them to snap. Sunspots are magnetic eruptions rising through the surface of the Sun, hurling electrified gases far into space and emitting intense ultraviolet radiation, often in the direction of the Earth. Uh-oh. Well, have no fear, Earth's differential rotation protects us. Not only does our Earth rotate differentially on its surface, but also down into its center. Studies of seismic readings of shock waves from earthquakes indicate the metallic core of the Earth is rotating slightly faster than the surface of our planet. Scientists think that the differential rotation of Earth's magnetic core within the slower rotating metallic liquid creates the magnetosphere arising from Earth's poles and extending far out into space. This magnetosphere keeps Earth safe from electrified gases from the Sun. Hurrah for rotation! Far out! Now, the 9.0 megaquake in 2011 off the coast of Japan rearranged the mass of Earth's crust and caused the rotation of Earth to speed up. The day got shorter. Not much shorter, 1.6 millionths of a second, but we are accustomed to seeing the Earth's rotation slowing down. The Earth rotating through the tidal action of the Moon's gravitational effect on the oceans drains kinetic energy from the Earth's rotation, causing the planet to slow down. Each day is becoming longer, about 2/1000ths of a second longer. Well, I need to adjust my watch. Leap years, we all know, are when we add a day to the calendar every 4 years, on February 29th, to straighten up Earth's yearly rotation around the Sun, taking 365 1/4 days. But leap seconds are added to the clocks every so often to synchronize our clocks with the slowing rotation of the Earth, and allow the Earth to catch up with our clocks, as if the Earth is concerned about our timepieces. 27 leap seconds have been added since 1972. The last leap second was added on December 31, 2016, and made the clocks read 6:59:60 p.m. Yeah, I didn't notice either. But the Sun's rotation has unexpectedly been speeding up recently. Usually it takes 86,400 seconds for the Earth to rotate, as measured by an array of atomic clocks in different locations on Earth and coordinated by a special service in Paris. Yes, they pay people for that. July 19, 2020 was the shortest day ever recorded, a whopping 1.46 milliseconds less than the usual 86,400. Gadzooks! If this keeps up for another 5 years, they may have to add a negative leap second to synchronize our clocks to Earth's increasing rotation. Computers and satellites won't like to see their clocks read January 1st at 0 o'clock, and they say time can't go backward. At least the Earth hasn't started rotating backward or stopped rotating altogether. That would be catastrophic. Everything would crash forward at whatever differential speed it was rotating on Earth. Yet that appears to be what happened to the planet closest to Earth, Venus. Venus rotates very slowly backward, in retrograde, and that is very unusual. How so, you ask? Well, there are several theories to why Venus rotates in retrograde motion, while all the other planets rotate in prograde or forward motion. Liquids inside a rotating sphere, like a planet, have a lot of inertia. That's why when you take an egg from the fridge, for example, and try to spin it, it won't spin. The liquid inside is just sitting there. Its inertia is resisting your attempt to spin it. However, if finally, after many turns, you manage to get the raw egg to rotate, it's hard to get it to stop spinning. If you do pick it up and put it back down, the egg will start rotating again, because the inertia of the liquid inside it is still going forward. You only stop the shell from spinning. Something like this may have happened to Venus. Wait a minute. Venus? Backspin? Tennis? I think there's a connection here, somewhere. We know that on Venus, the planet, one day is longer than 1 year. It takes longer for Venus to slowly rotate around backward one time than it takes Venus to orbit the Sun once. But Venus is slowing down dramatically, and by 6.5 minutes in the last 25 years. If there still is liquid inside Venus and the movement continues, we might see Venus completely stop spinning backward and start rotating forward again. Come on, Venus, let's get with the crowd. This business of retrograde and prograde rotation has got quite a bit of mystery to it. It seems that everything tends to rotate in prograde motion. If you shape your right hand like a ball and stick your thumb up to indicate north, then curl your wrist towards you, that's prograde motion. Your fingers on the left side of your hand are moving towards you. Black holes, solar systems, galaxies, atoms, stars, etc. all seem to rotate prograde, depending on which angle you view them from. Experiments at the Large Hadron Collider indicate that subatomic particles spin toward the left, prograde. It's starting to look as if we may be in a left-handed universe. Then why is it so hard to find a left-handed manual can opener or measuring tape? I don't know. It's a mystery.
It's 2065, and you're standing on the moon's dusty surface, working away on the latest array of solar panels to help fuel the local town's energy grid. Suddenly, the surface begins to shake. Is this a moonquake? Or are those moon-born teenagers having a party in the town hall again? You look up at Earth. You're so used to it, you barely even notice it anymore. But now, it looks different. It takes you a few moments to work out why. It appears to be shrinking. You begin to panic. The Earth is moving away. The ground rumbles again, and you work out what's happening. The Earth isn't moving, but what you're standing on is. The moon has broken off its orbit and it's heading out into deep space. Destination unknown. The strange thing is, it's happening right now, and has been for a very long time. It's even affecting how long our days are. Eventually, it will pull away altogether and dramatically affect our planet's oceans. To explore what will happen, let's go back a little, to put it all into perspective. The moon has been hanging around us, literally, for 4.51 billion years. There are a few theories as to how the moon came into being. The main one is that it formed when a large object smashed into the young Earth. The early solar system was a chaotic place. A number of stellar bodies were created that didn't make it into a full planet. One of these bodies, as large as Mars, smashed into Earth, throwing huge chunks of our planet's crust into space. Gravity took over and tied these separate elements together. This explains why the moon is made of lighter particles than we find here on Earth. Billions of years later, and we're more than used to having the moon with us. It affects so much of our everyday life. The obvious one is tidal motion. The gravitational pull or tidal force that the moon exerts on our planet creates the tides. This force causes all of the water on the Earth's surface that's closest to the moon to bulge out to one side. A very short explanation is that it pushes in from the top of our planet and also the bottom, while pushing out from the sides at the same time. The Earth also has an effect on the moon, which we'll get into in a minute. But it appears that the moon might not like our company as much as we might think. It's slowly drifting away from us, even as we speak. The moon can seem small or large depending on the lunar cycle, but in actuality, it's just over a quarter or 27% of the size of Earth. The diameter of the moon's orbit around us is nearly 477,213 miles, but this diameter is increasing by 1.5 inches every year, which of course means that it's moving away by a factor of 1.5 inches each year. To help explain why we have to analyze our relationship to the moon a bit more closely, both celestial bodies are tidally locked. We are synced up in such a way that we always see the same side of the moon. The hemisphere that we never see is often referred to as the dark side, but that's not quite right. As the moon orbits Earth, different parts are in sunlight or darkness at varying times. This change in illumination is the moon going through its various phases. The tidal forces not only affect our oceans, but the body of the Earth too. Because the Earth is more rigid in structure than water, the tides on more solid matter, like the Earth's crust, have a much smaller effect. The tidal forces are interdependent. The gravitational field of the Earth will also apply tides in the body of the moon. Again, because we're not talking about fluid, the effect is very small, but it's there. This interchange of tides is quite complex. Interiors of both bodies are heated by these tides, just as the force applied to any object can create friction or its own heat. Take the planet Jupiter, for example, and its moon, Io. The tidal forces of the giant planet are so huge that the surface of Io, which is solid, is raised and lowered several hundred feet in each rotational period. The heat generated means that the interior of Io is most likely molten. As a result, the surface of Io is covered with active volcanoes. It's one of the most geologically chaotic places in our solar system. Despite its heat, it's definitely not the place to take the family for a summer holiday. Back to Earth. Our planet rotates on its axis once every 24 hours, and the moon performs one revolution around us in 27.3 days. The bulge on Earth actually speeds up the moon. The Earth pulls the moon ahead in its orbit. In other words, the Earth's bulge increases the radius of the moon's orbit around us. While this is happening, the moon pulls back on the tidal bulge of the Earth, slowing its rotational speed, though just a fraction. A very small fraction. This means that 100 years from now, a day on Earth will be 2 milliseconds longer than it is right now. Blink and you'll miss it, literally. In addition, since the Earth is larger, the gravitational pull is stronger, causing the moon to speed up slowly. As time passes, its orbit will become bigger and bigger. This takes us back to that measurement of 1.5 inches. It may not seem like a lot, but over a period of time, this measurement becomes significant. Let's jump forwards billions of years from now, where we see that the moon's orbit is so big that it does leave the pleasure of our company permanently. What happens to our oceans then? You've already guessed it. The tides will cease to be. That will make for very calm seas for any boat trips. That's if there are any humans left in, 50 billion years. Before that time, because of the tidal locking slowing down the Earth's rotational speed, it's possible that the Earth will slow down enough to permanently face the Moon. In turn, it may prevent the Moon from moving away from us. Imagine the effect on our planet if we stop rotating. One half will always be in darkness, the other in light. That'll play havoc on our seasons and the natural life. While it sounds dramatic, and the loss of tides would be a significant phenomenon, there are other more serious things to worry about occurring before then. In a tenth of that time, 5 billion years, our Sun will likely consume both the Moon and the Earth. Yep, our Sun is going to have a galaxy-sized party, the likes of which our solar system has never seen, and everyone's invited. The Sun is continually burning the hydrogen in its core into helium. Right now, it's approximately halfway through its life cycle. Towards the end, it will run out of hydrogen in its core. The Sun will ultimately become a red giant. Its surface is predicted to reach Mars. That's when gravitational forces will take over. The Earth will be dragged into this new Sun and disintegrate. The Sun gets 10% brighter every billion years. So long before the planet is totally destroyed, the heat will have melted any ice and fried almost everything living. All of our oceans will have dried up too. So, while the planet has a 5 billion year life cycle yet, everything living on it may only have a billion. To recap, the Moon may move from the Earth, but the Sun will have wiped out both long before the tides are halted. Let's steer away from that hot object and return to that sibling-like relationship of the Moon and Earth. The fact that the Moon has the same rotational period as the orbital period of both the Earth and the Moon is no coincidence. Over billions of years, the tidal coupling of the two has led to the synchronization we know today, and yet it's still evolving. The Earth is slowing its rotational period. Eventually, it will match that of the Moon, and they will be exact. And as I mentioned before, the days on Earth will become longer as well, by 2 milliseconds every century. To have a significant impact, it will take many thousands of years. However, it's nice to think that both the Earth and the Moon affect each other in many powerful and beneficial ways. It's almost like they're simply hanging out together, like a couple of old intergalactic buddies.